Hello and welcome to Creo 4.0 Spark Analysis Extension. I'm Joshua Fontana and we'll be doing a presentation today. So as far as the webinar agenda here, we'll do a short introduction of who Boundary Systems is, and then we'll jump into the Spark Analysis extension, going over what is the extension, setup, determining values, other design considerations, and so on. And then we'll do a Q&A. So Boundary Systems is a tech leader whose partners include PTC, Solid Thinking, eTraj, ZWCAD, and other tech companies. We're known to be the 16th fastest private company in the Cleveland area, whose capabilities include product lifecycle management, data management, CAD design and consulting, simulation, and product development. As far as some of our accolades are concerned, some of our awards consist of the Inc. 5000 and Weatherhead 100 and other accreditations, including the Windchill Certified Implementer, PTC Preferred Service Provider, and a PTC Certified Training Partner, so we can handle all of your training needs also. Some of the solutions that we offer, of course, come from PTC as far as Creo Parametric and other Creo products, Solid Thinking, eTraj, and ZWCAD, which would be our 2D AutoCAD-esque software. So if you have any questions, feel free to toss me an email. Again, my name is Joshua Fontana. You can email me at jfontana@boundarysys.com. Or if you have any sales-related questions, you're wondering how much some of the products cost, feel free to email Mike Kotlowski at mkotlowski@boundarysys.com. Okay, so let's go ahead and jump into what is the Spark Analysis. So the Creepage and Clearance analysis. Okay, so that's essentially what the Spark Analysis tool does. So this allows design engineers to electronically analyze their designs to identify if electrical components are violating insulation rules. Okay, so there's two types of analysis. The first type is the clearance analysis, which is to identify the shortest distance between two conductive parts or between a conductive part and the outer surface of an enclosure when the distance is measured through air. Okay, so the second analysis is the creepage analysis, and this is to identify the shortest path between two conductive parts or between a conductive part and the outer surface of an enclosure when it's measured the path along the surface of the insulation. Okay, so there's a depiction of both the creepage and clearance analysis there. So because most people don't have automated solution for analyzing 3D electromechanical assemblies, it is not uncommon for designers to fail to fully investigate a design. Either the analysis was deemed unimportant or it's simply too difficult. Thus, the designers had to rely on experience and ultimately a physical prototype. Identifying an electrical problem at the prototype stage is, of course, very expensive and can have catastrophic consequences. Again, because most people don't have a solution to electrically analyze a design, designers have traditionally relied on rule of thumb. So for simple designs, this is okay. However, as designs become ever more complex and more reliant on electrical components, there is a high probability a failure will occur. So let's look how you set up your models. So first, you have to set up the conductivity of the component, and to do this, a parameter is added to the component to describe the comparative tracking index, or a CTI value. Once the parameter is set in Creo parametric, we'll understand whether the component is conductive or non-conductive. As a safeguard, components that are missing the CTI value, they're automatically set to being conductive. So the clearance and creepage assumes that the component is conductive. So it's a worst case scenario. For components such as fuses, there is the flexibility to define quilts for a conductive area while the rest of the part is non-conductive. To further improve the performance during the validation of design setup, colors are temporarily assigned to components with different CTI values for visual recognition. The clearance and creepage file, which can be either a CSV or a text file, is used to define all the nets which will exist in a design, as well as the minimum distance which is required to provide a suitable functional insulation. The file also determines the maximum groove width for gaps, which will cause a short circuit. The file is used to analyze and help to automate the assignment of components in their respective nets. The analysis allows the users to determine the type of analysis to be performed and what nets for components or quilts to be analyzed. The analysis criteria has been designed to be as flexible as possible, allowing users to optimize the analysis time. For example, if the design is to be refined to solve a particular electrical problem, the users can simply analyze a two-component, improving the performance of the analysis. Once the analysis is complete, the validations are displayed for further investigation. So when a validation is selected, the part will display in the graphics window to help the user better understand the failure. So as you can see there, it shows the path it took for that error to occur. Users may also override the results and ignore the validation. By doing so, the user's name is stored in the assembly along with a note which will describe why the validation was overwritten. Lastly, the analysis results are stored with the assembly for later design reviews. So you don't have to bring in the information every time you want to view the results. Okay, so first of all, we'll talk about some design considerations, okay, so which include computer hardware and some model setup. So similar to any analysis application on the market, for efficient clearance and creepage analysis, you must prepare the CAD model. It is likely your CAD model contains small part details that are essential for manufacturing purposes, but meaningless for the purposes of the analysis. Removing unnecessary geometry will help improve the mesh time, reduce memory consumption, and increase the reliability of the analysis. So here's the recommended computer hardware. So you can see for designs over 200 parts, of course, a 64-bit operating system is good to have. 32 gigs of RAM or higher, and a swap space of 200 gigs. So for units, all units should be consistent within your assembly, okay? And the accuracy of all the models should be set to absolute with a consistent value. So it's also nice again, so it will decrease mesh time to remove all parts that will not be affect the analysis to improve the performance. Same type of thing with the removal of small surfaces and features like chamfers and cuts to reduce the size of the model that's going to be analyzed. Another good thing is to remove all your cable harnesses. Okay, so there's a lot of features associated with the actual harness, so it's nice to remove those so they're not getting analyzed. Also, removing surfaces that will not affect the analysis to increase the success rate of mesh creation. Okay, so as far as the analysis is concerned, it goes in this type of process. Okay, so first is this discretization. So this process is the process of transferring continuous functions, models, or variables and equations into discrete counterparts. So in this case, the boundary box of the assembly is divided into smaller boxes, starting with a slightly enlarged outline. So the boundary box of the assembly. So that's what I have there in the first image on the left. So the box is then bisected in each direction, yielding 8 cubes. So that's the one in the middle. So each cube then is bisected again. So it keeps on doing this divisional process until either a box is empty, that is, it does not have intersecting of any surfaces of the model, or the box is less than the mesh size. So a smaller mesh size value will yield more accurate approximations of the assembly, but will result in many more boxes and consequently a performance decrease. So we see here, as I explained, that the first box on the left starts off with the entire assembly, and then it divides it up again and again. So the next part of the process is the graph creation. So each one of those boxes, the corners become nodes, and then each edge becomes lines, okay? So that creates the essential graph. And then at the end, it actually runs the algorithm with a modified Dijkstra's algorithm, which allows it to find the path from A to B, okay? And while I was doing some research here, I noticed another algorithm that's very possible, and it's very, very close to Dijkstra's algorithm, which is the A-star algorithm, okay? So those of you that are familiar with mathematics, then these two types of algorithms are used to find the shortest path between objects. Okay, and then we'll go ahead and go into the demo. Okay, so here's our part. Let me get this set up a little bit. Okay, so here we have a switch. So we have this insulative material that consists of the base, and then we also have some conductive materials over here. So we have lines coming in here and so on. So here we can go to analysis, and here we see the clearance and creepage analysis. So I'll go ahead and select that. So first of all, we need to bring in our clearance and creepage file. So if you don't have this file, then you can simply select quilts for the net pairs, and then just put in and specify thresholds for the clearance and creepage and groove and run the analysis that way. But if you're checking multiple parts, then it's good to have a clearance and creepage file. So we'll go ahead and grab this file real quick. So in this case, it's just an Excel file, and we'll say open. And as this is importing, let me show you what is in that file. So here's that Excel file that I just brought in. As we see, there's just DCP, DCM, and their available or their allowable distances. Okay. So we have that for clearance and creepage, and we also have groove widths here. So that's what's inside of this file that I'm bringing in now. Okay, so now we see that is in. So now what we can do is start setting up the nets. So we'll go to setup and then say nets. And here's a dialog box associated with that. So here we have DCP, DCM, and then ground. So for DCP, we're going to go ahead and select the individuals tab and then just select the two components for that. So for the components here, we'll select these two components. Okay, so it's those two components. For DCM, we're going to go ahead and select sets and then add some. So here we'll select sets and then select this component. Oops. So after we have sets created, then we can grab that as the seed component and then find the other connective components. We'll do the same thing with the ground here. So we'll add a set there and select this component here and say find, so it finds other conductive components associated with that. So we'll hit apply, and now we see those are all there. And we'll say OK. So let's check out the comparative tracking index number associated with these parts. So I'll select on the part here and then go to parameters and view the parameters of this part. Okay, so here's the part parameters as we see for this part. And if we scroll down to the very bottom, we do see this comparative tracking index number here, okay? And it has a value associated with 0, indicating that it is conductive. So any value over 0 will allow it to be insulative. So we'll go back into the clearance and creepage here. And then set up the nets. Okay, so we'll go to Setup and Nets. So these have all been determined. That's good. And net pairs. So here we want to just check all of them here, and we can just check them all automatically by selecting pairs all nets, because we want to analyze them all. Okay. So we'll go to options also and view the options. So here we have for the clearance mesh size, we use the default, and the default here for the creepage mesh size, and the validation or the violation tolerance here. So we use the default there. So that's all fine. Okay, so now that we have this all set up, we're also going to check the worst violations here. And then we're ready to go. So we can say compute. So of course, this takes a little bit of time to compute the clearance and creepage here, because it's essentially going through that process of breaking down the volumes into smaller volumes, again, like we talked about, and then it's running those two types of analysis. So it's going through that Dijkstra's to find the shortest path between A and B. It seems to be taking a little longer than it has before. Oh, there we go. So here is our results here. So here we see some violations between DCP and DCM. So we can select on the violation here and see the distance and the threshold. So the distance is less, so that needs to be rectified. So we both have clearance and creepage up here at the top. here the ground is actually okay. So we check out the ground value here, and we can see it gives us a graphic representation of that path it took. Okay, same with the rest of these. Okay, so we do see plenty of violations here, so we'll say okay here. And then what we need to do is actually modify this part, the base part, so that it does not have those violations. So we'll go ahead and select this base part and activate it. Okay, so now that it's active, we can go ahead and modify the part. So let's select on this feature here. We'll modify this dimension to 1.5 and this height value of the base at 3.5 to add some distance there. And the height of this web feature to 12 units. And then we'll go ahead and regenerate. Of course, you could also utilize flexible modeling to simply push and pull on these features. I thought about that for a workflow also. So now that that has been modified, we can go ahead and reactivate the top level and rerun the analysis. So we'll go back to Analysis tab and Creepage and Clearance. So you'll notice that it still brings in the same Creepage and Clearance file because it's associated with this assembly. So you don't have to bring in that file every time and reset up your nets and everything like that, because it's all just built in right into the assembly at that point. So once that's done and everything's already set up, we can hit compute again. Hopefully this one runs a little faster. And you can see it running down here at the bottom too. is doing step 2 of 2. It's 78% done. So it's going through there. And now it's doing a graph creation, as you see. Okay, so it looks like it's on net pair 3 of 3. So it should be done pretty soon. Okay, so now we see that some of the colors have changed within our net pair violations dialog box. So this one here, the threshold, is okay now. This one is, we have a distance of 9.177 units, and the threshold is 10. So we can override this to make sure that, or just to say that it's okay. So if we want to override that, we can check the checkbox here. It puts in my name and date, and then we can override it and say that it's okay. Or put some other description in here, okay? So we notice the color changes also indicate that it has been overwritten. Same with the creepage here. So we have these two that have been okay now, and this one is again very close. So we could either go back and modify the part again or determine that it's okay or allowable. So the other thing I want to show you real quick is the info all. So if you wanted to export this information out to a text file, then that's what we have here that shows the violations and the distance between the components. So if you need to put this in your engineering report, you can do so. Okay. So that's what the clearance and creepage analysis extension, or the Spark analysis extension, does for you. So that concludes the demo portion. So in summary, clearance and creepage analysis enables engineers to fully analyze in a virtual prototype and find issues prior to manufacturing, then optimize the design throughout the approved workspace, material, and etc. So clearance and creepage analysis also ensures product safety, reduces the product cost, and time to market. So again, my name is Joshua Fontana. If you have any further questions, feel free to contact me. And also, my sales guy here is Mike Kotlowski, and you can contact him for any further questions. The other thing I wanted to show you is feel free to go to the Boundary Systems website here and view our other what's coming up for us in the future here in our events. So let me close down Creo Parametric here so it's not eating up my system resources. There we go. So here we have products, services, training, and events. So if we select on events, we have hands-on workshops and webinars. So you can view our schedule of our hands-on workshops and webinars and then register for either one of those events that are coming up. Okay, I want to thank you for your attention today. And again, feel free to contact me if you have any questions.